Hey guys, today we're going to be doing parallel circuits in RLC. So let's just get straight into it. But first, let's start with the refresher here. Okay. Alright, so we have a resistor. And the equation for a resistor is V equals IR. Probably the most popular formula in EE. Then we have the inductor. And this formula is V equals L di dt. And we have a capacitor. And the formula for this is I equals C dV dt. Okay? And then parallel RLC circuit is going to be where all the components share the same two nodes. So at the top here, draw a resistor, an inductor, and a capacitor, right? So this is parallel, and typically when we're analyzing these circuits, we're looking for the voltage across here. And for series, we're looking at all of them sharing the same current. So resistor, inductor, and capacitor. Sorry about my bad drawing, but as you can see, typically we'll add like a voltage source here, and as you can see, they all share the same current, right? So now that we've gotten that out of the way, let's move on to actual analysis. Or let's start with the characteristics of these circuits. So we have a parallel circuit. Okay. So I'm going to redraw it, with the resistor RL for inductor, and then C, capacitor. Okay, they all share the same nodes. Alright, we want to find the V here, because typically, if we know the V here, we can find everything else. We can find the current through resistor, current through inductor, current through capacitor, we can find everything. So, let's use KCL. KCL at this node, right? So we're getting used to this. Alright, and so we would have the current through the resistor plus the current through the inductor plus the current through the capacitor, and that equals 0, right? So we know that the current through a resistor is just V over R, right? And for the inductor, it's a bit tougher because it's not strictly in term. We actually have the derivative of the current, so we're gonna have to do some manipulation here. So I'm gonna move the L to the other side. Actually, I'm gonna move the dt as well. So we get di dt, or 1 over LV dt equals di. And so if we integrate both sides, take out the L, 0 to t, V. Sorry about that. So t, V dt equals di. And this is from I initial and I of t. So integrating, we get 1t v dt equals I of t minus I initial And so that would get us IL of t equals 1 over L 0t v dt plus I initial, I of 0, the starting current through it. There, let me add that. All right. And the capacitor, also much more easier. It's just C dV dt. All right. So, if you put them all together, we get V over R plus 1 over L 0t v dt plus I initial plus C dV dt, that equals 0. This should be our KCL equation with all of the stuff. So what I'm actually going to do here is I'm going to derive both sides, right? So we got 1 over R dV dt. Derivative of this, it's just an integral, so we can just get rid of that. So we have 1 over L V, and this is a constant, so that just goes away. And then we have C d squared dt squared equals 0. Alright, so I'm going to rearrange some stuff so we can get into our characteristic equation. Okay, move the d squared to the front, divide everything by c. And then we get this equation right here. Right here, this is our characteristic equation for parallel RLC. And so typically in the second orders, you'll find that you can put them into this form: 2 alpha plus, or dVdt plus W naught squared, this is the natural frequency, equals 0. And we'll go more in depth into what these are, because these are pretty new things, right? And so let's try solving the differential equation, right? So we had the equation d squared v dt plus 1 over RC dv dt plus 1 over LC of v equals 0. And so we're just going to guess that the solution, or guess, is, it takes the form a e to the st, right? We're just going to guess. Alright, so if we do that, we get a e to the st times s squared plus 1 over RC. Oh, let me actually just put a to the e to the st times 1 over RC times s plus a e to the st plus, or not plus, times 1 over LC, right, equals 0. And so if we divide both sides by e to the st, we can simplify this to s squared plus 1 over RC s plus 1 over LC equals 0. Alright? And so you can see that this right here is our characteristic equation just in the s. And so these s's will be the solution to, or that would be the roots for our exponential here. And so, oh, one sec. So we'll see that v of t will equal a e to the s1t, our first root or first solution from this quadratic, and b e to the s2t, right? And so just keep moving down. All right, so we have that, we have our solution, but what if our roots are complex? Because we know that sometimes in a quadratic, the roots will be complex. So what happens then? Okay. And so we're gonna let S be some real component plus B, J. This is our real part, and this is our complex part. Using J, same thing as I, just in EE, we typically use J. Alright, so that means we would have A to the, or times E to the A plus BJ times T from our solution. Alright, and then we're going to split this up because when you add, when there's addition in the exponent, we can multiply them out, right? So this would just be AE to the AT times E to the BJ, right? And so this is where I'm going to show Euler's identity. Okay, and so what this is, it's just saying E to the J theta equals cosine theta plus J sine theta, all right? Right, and so there's a bunch of complex math behind this, and we're going to use this complex math. We don't need to know it, how it works, but we just need to see that when we have a complex component inside the e exponential, we actually can find sinusoids, right? And so if you change that in, we get e to the AT times, or sorry, I forgot the t here. Let me just erase that. J times t, right? We actually get cosine bt plus j sine bt. And so we have, you'll see here we have a sinusoidal component here, right? And so that means if our roots are complex, we will have a sinusoidal looking form for our solution. So if we continue the math here, if we do it for the other root, then we would get the form v of t equals a cosine, or a e to the negative at. We'll get to what the a here in the next part. Cosine bt plus b e to the negative at sine a of t. Okay. So now that we know that, we can find our parameters, right? So we have the parameters of an RLC circuit, specifically the parallel version, because that's what we're doing today. Okay, so I showed you this before, or just exposed you to it. This was our original characteristic equation, but typically in second order systems, in any second order system, like spraying or dampening, just any, or not that, any alternating thing, can simplify it to this. S squared plus 2 alpha S plus W naught, which is the natural frequency squared, right? And so, if you compare this to our circuit equation, we can find that alpha is equal to 1 over 2 RC, and that our natural frequency is equal to 1 over square root LC. Alright, and so these are very important and makes finding our solution a lot more easier, because you could try and solve this quadratic, but you know, the quadratic formula is kind of annoying to type in your calculator. So here we have the parameters of the circuit. And these are really important because if we know these parameters, we can know exactly how the circuit will behave, right? So if we know the parameters, sorry about my bad handwriting, we know how the circuits will behave, okay? And so, go into more in depth, or let me make a new page. Okay, so that brings us to damping, all right? Damping. So the 3 types of damping, okay? We have underdamped, critically damped, and overdamped. Okay? And so, let's go on to when we know our circuit will be these 3, right? So, our circuit will be underdamped when alpha is less than our natural frequency, right? So back to, let me write alpha again. So 1 over 2 RC, and W naught is 1 over square root LC. So when our alpha is bigger than our natural frequency, that means our circuit is underdamped. So what this means is that we'll have complex roots. So like some examples would be 3 plus 1j, 2 plus minus 6j, or any sort of conjugate, right? And so what that means, as we talked about before, is we would have the solution form of ae to the alpha t cosine wd t plus b negative alpha t sine wdt. And so you haven't seen WD, and so what WD is, or the damping frequency, or the damped frequency, is square roots of our natural frequency squared minus alpha squared, right? And so that's the underdamped case, when our alpha is less than our W naught, because alpha is typically the strength of your dampening. So if it's not strong enough, then it'll actually oscillate, right? So let's go on to critically damped. And so this happens when our alpha equals W naught, right? So the cool thing about critically damped is that this causes the circuit to go as quickly as possible to 0, or its resting point, right? So basically this means that we will have real and repeated roots. So some examples, you'll have like negative 500 or negative 2 or like negative 1000. You'll typically see in your problems that they're much larger than these numbers, but I'm just throwing them out there. So this will take the solution form of, let me just block that out. So v of t equals a e to the negative st, and or plus b times t negative st. Where this t came from is some diffie q stuff, not really in the scope of circuits, but just know that it is there and critically damped. Alright, and so that brings us to overdamped. And so if you look at the others, then this means when A or alpha is not equal to, is greater than our natural frequency. So this means we have two real distinct roots. Okay, some examples be like negative 3 and 2, negative 2, negative 1000, and negative 4000, something along those lines. Again, you'll typically see on the orders of like 10 to the power 3 or 4. I'm just throwing some numbers out there. Right, so this should take the solution form. This was our first case where it was simply v of t equals a to the e s1t plus b e to the s2t, right? Where s is equal to negative alpha plus minus WD. And in this case, our damped frequency, or WD, is just alpha squared minus W naught squared. Notice how in this one, the alpha is first because it's bigger than our natural frequency. And this just makes it so that it's not a complex number, because then if natural frequency was bigger, then this would be a complex number with an I. Alright, so let's go over an example. So where's the hand tool? Alright, an example. So what type of damping does this parallel circuit have? Okay, so we're gonna have our resistor equal to 100 ohms, our inductor equal 50 millihenries, and our capacitor equal 0.2 microfarads. Alright, so we need to get our parameters for the circuit, and we just need our alpha and our W naught, our natural frequency. So 1 over C. Okay, and so if we plug that into our calculator, we will get 12,500 radians per second. That's the unit of our alpha, also known as a neper frequency, some terminology you might hear. And our damped frequency, or not damped, sorry, our natural frequency is 1 over LC, square root of LC. If you plug that into our calculator, we get that this equals 10,000 radians per second, right? And so now it's time to compare alpha and maybe not. And so we see that alpha is greater than our natural frequency. So this is overdamped. Okay, and that is our answer.